Hello students, welcome to a session with time. Now in this session we are going to discuss nucleophilic substitution, which is part of chemistry, organic chemistry to be particular. Now this nucleophilic substitution is a well-known concept which is asked in the board exams and entrance exams. And I hope this session would be useful for you, right? So shall we begin? Now this is our YouTube channel, Time for IIT JEE NEET, where you'll find interesting videos covering all concepts, important concepts which are useful for your board exam as well as entrance exams. So if you have noted this YouTube channel, we'll start now. Now as we said, we are going to discuss nucleophilic substitution. So what are nucleophilic substitution reactions? Before we begin, let us look at what is a nucleophile. A nucleophile is an electron rich species. A nucleophile is an electron rich species which may have a negative charge or a lone pair of electrons. So a nucleophile is electron rich, having either a negative charge or a lone pair of electrons to offer. So it is an electron pair donor. So it is going to donate its electron pair, which is in the form of a negative charge or in the form of a lone pair. Now what do you mean by this substitution? Substitution means replacement. Replacement of a similar nucleophilic species on the reactant. So a reactant is having a nucleophilic species on itself, which is going to get replaced by this new nucleophile. So the new nucleophile we can call as the incoming nucleophile. And the one which is already present on the reactant is the outgoing nucleophile. So the incoming nucleophile is going to replace the outgoing nucleophile, and replacement is nothing but a substitution reaction. So in a nucleophilic substitution reaction, as you will see here, which we are doing only on haloalkanes. Now there are many species which undergo nucleophilic substitution reactions. Our focus is on haloalkanes, right? So haloalkanes are what? They are alkyl halides, where the halogen is attached to an sp3 hybridized carbon, right? So an alkane means it is sp3 hybridized and the halogen is present on this. And because it is sp3 hybridized, we have only a single bond. When we have a single bond, we cannot have an addition reaction. Addition reactions require multiple bonds. And this is a substitution reaction, which means that you are not going to have a addition taking place. You are not going to have an addition taking place because there is no multiple bond. So we have only a single bond. So there is a substitution reaction. So let us check what this nucleophilic substitution is about. The halogen that is attached to this carbon is more electronegative, and therefore that bond, that is a CX bond. So shall we take this bond as CX, right? The X is the halogen, right? That bond is a bit polar, where the carbon is having a slight positive charge and the halogen will have the negative charge. So the CX bond being polar, right, making carbon slightly positive, will see to it that a nucleophile, what is a nucleophile? Electron rich species, right, will see to it that a nucleophile can attack this carbon. So this carbon is being attacked by a nucleophile because this carbon is positive charge, means slight positive, because the halogen is slight negative. So because halogen is electronegative, more electronegative than carbon, the CX bond is polar, carbon having a small positive charge attracting a nucleophile. Next, this small positive charge will see to it that the carbon is attacked by a nucleophile. Now what is present on the carbon already? That is a halogen. So halogen is the outgoing nucleophile. So halogen is the outgoing nucleophile, and the incoming nucleophile, which we can symbolize as Nu. The Nu is going to attack this carbon and the X is going to go out, right? So the halogen, that is a halide ion, is being replaced. So a new bond is formed between the carbon and the nucleophile. Clear? So when a nucleophile comes and attacks this carbon, right, the halogen is going to go, which is the outgoing nucleophile, and the incoming nucleophile is whatever is the nucleophile. It could be an OH minus, it could be a CN minus, it could be NO2 minus, right? Any nucleophile is going to replace the halogen. Can we represent a reaction, right, nucleophilic substitution like this? The carbon halogen bond is there and the nucleophile has come to attack, right? Now the CX bond is cleaved heterolytically and the halogen is coming out as what? Halide ion. Halogen is coming out as halide ion and the nucleophile is now taking the position of the halogen. So taking the position means what? Replacing the halogen. So it is a substitution reaction. So a substitution reaction can be shown like this, where a nucleophile has replaced the halogen. Now, shall we say that a stronger nucleophile replaces a weaker nucleophile, right, in a nucleophilic substitution reaction? I hope this is clear. So we have now checked what is a nucleophilic substitution reaction. So an incoming nucleophile is going to replace an outgoing nucleophile. The incoming nucleophile is a stronger nucleophile and the outgoing nucleophile is a weaker nucleophile. That is what you are saying, that a stronger nucleophile is going to replace a weaker nucleophile. Clear? So among the nucleophiles, we may have nucleophiles of various types. You may have a CN minus, you may have an OH minus, you may have simple water. Water itself is a nucleophile. You may have an NH3, right? NH3 will have a lone pair, water will have a lone pair, whereas the other things are all having negative charges. CN minus and OH minus are having negative charges. Clear? So we find here that nucleophile is offering its electron density either in the form of a negative charge or in the form of a lone pair. Clear? There are some nucleophiles where the donating atom or the donor atom is different, right? Such nucleophiles are called ambident nucleophiles. Ambi means variable. So ambident nucleophiles are those where the donor atoms could be different. For example, CN minus can have a carbon attacking or a nitrogen attacking, right? Similarly in NO2, you will find an oxygen attacking or a nitrogen attacking. Let us check that part. Now ambident nucleophiles will have two nucleophilic centers, right? In cyanides, let us check what are all the donor atoms, a carbon as a donor or a nitrogen as a donor. When carbon attacks, we get a nitrile or a cyanide. When nitrogen attacks, we get isocyanide or isonitrile. Clear? So when the carbon is attacking this carbon, so let us say that it was Rx. The Rx is being attacked by a Cn minus with the carbon end attacking the R. R is the alkyl group. This is an alkyl halide. Alkyl halides are also called haloalkanes. So the bond that is formed is between R and Cn. So we get RCN. This is nothing but a cyanide. Similarly, if you have the Rx attacked by a nitrogen, the nitrogen part, right, then we are going to have RNC. We'll have RNC, which is isocyanide. So we get a cyanide or an isocyanide depending on what atom has donated its electron pair. Clear? Similarly, look at the nitrite ion. Nitrite ion can have oxygen as the donor or nitrogen as the donor. Oxygen has got a negative charge and nitrogen has got a lone pair. So when oxygen attacks the Rx, what are we going to get? We get RONO. RONO is a nitrite. And when the nitrogen attacks, we get RNO2, which is a nitroalkane. RONO is nitrite, alkyl nitrite, and RNO2 is a nitroalkane. So we can have ambident nucleophiles wherein the donor atoms could be different, right? and what we find is that the product formed will be different depending on the donor atom. So if carbon donates in the cyanide, we get cyanide, which is also called a nitrile, and when nitrogen donates, we get isocyanide or isonitrile. Clear? So we have also seen the case for nitrite, where nitrogen or oxygen can be the donor atoms. Now, having said all this, we are now in a position to discuss the mechanism. Now, these reactions, that is nucleophilic substitution reactions, can be of two types. Broad classification. They could be either SN1 or SN2. That is what we know, isn't it? We know nucleophilic substitution as either SN1 or SN2. So, what is this mechanism that we are talking about? The first one is the SN1, which stands for substitution nucleophilic unimolecular. This is a very, very important thing, unimolecular. So, in that particular step, there is only one molecule participating. It's a nucleophilic substitution, but it is unimolecular. So, that one stands for unimolecular. Now, how is the rate dependent on this concentration of alkyl halide? It is dependent only on the concentration of alkyl halide, not on the concentration of the nucleophile. Nucleophile is also coming and attacking, but then the SN1 rate is depending only on the concentration of alkyl halide or the haloalkane. How can we show this? Rate is equal to K into concentration of the alkyl halide, which is given as Rx. Actually, there is a power 1 here. So, it is also a first order reaction. From chemical kinetics, you know that when you have the power as 1, it is order 1. It is first order reaction. It is also a unimolecular reaction. It's only a coincidence, right? All unimolecular reactions need not be first order, but in this case we have found that order and molecularity are matching. Clear? So, let us look at what is happening in this SN1 mechanism. Now, the reaction takes place in two steps. The first step, what is going to happen? The alkyl halide, which is Rx, is breaking down into a carbocation and halide ion by ionization. So, Rx is undergoing what? Heterolytic cleavage. Heterolytic cleavage will give R plus and X minus. So, X minus is coming out first. So, R plus, right, if it is stable, it will be formed easily, right. So, this SN1 mechanism happens only when the carbocation is stable. Keep that in mind, right. Next thing is, we said that there are two steps in this reaction. What is the first step? First step is the alkyl halide undergoing ionization. Ionization is nothing but heterolytic cleavage, right. This is the slow and rate determining step. So, in this slow step, there is only one molecule participating, that is the Rx. Therefore, it is a unimolecular reaction. The slow step is a rate determining step, and in that step, there is only one molecule participating, and therefore, that is what? A unimolecular reaction. So, the concentration of alkyl halide is going to decide the rate of SN1 reaction. What is the next step? Next step is a fast step, right? Fast step means the reaction is happening in no time. The moment a carbocation is formed, the carbocation will take the nucleophile and then form the product. So, that nucleophile is attacking this carbocation to give the form of final product. Now, what substance will form a stable carbocation? Tertiary. So, among the alkyl groups, we know that tertiary carbocation is more stable than secondary, is more stable than primary because of hyperconjugation, is it not? So, tertiary alkyl halides will easily form carbocations, therefore, they undergo SN1 type of mechanism. Clear? So, here the nucleophile is actually waiting for the carbocation to form. So, it is not an attacking nucleophile. So, it is just waiting for the carbocation to form. So, it is not in a hurry, right? So, it is not an attacking nucleophile. So, for an SN1 mechanism, we need a nucleophile which is not attacking. Next thing is, you have to stabilize the ions, right? What will stabilize the ions? A solvent which is polar and which is protic, such as water, alcohol, right? They have the H plus, that is a protic. Protic means what? H plus, proton. So, polar protic solvent, right, is going to make the SN1 reaction happen easily. So a solvent needs to be polar protic to stabilize the ions that are formed in the first step, R plus and X minus, right? Then the nucleophile, right, is not an attacking one. So the nucleophile can be covered by the solvent, right, because it is not an attacking nucleophile, unlike what happens in the next mechanism that you are going to see. So this is an SN1 mechanism which takes place in 2 steps. We should say minimum 2 steps, because once a carbocation is formed, it may undergo rearrangement. Clear? Now this is what is going to happen to this alkyl halide in the first step. The CBr bond is breaking heterolytically in a slow step, forming the carbocation and the Br minus, which are stabilized by a polar protic solvent. Clear? That is why we need a polar protic solvent for an SN1 mechanism. What is the second step? Second step we have already mentioned here, that it is a fast step. So what is that? The fast step is the ionic combination. You know that ionic reactions are extremely fast, right? It's an ionic reaction. So the nucleophile, which is OH minus in this case, is taking up the carbocation to form this product, which is an alcohol. Clear? So step 2 is a fast step. The rate is not dependent on this step. Rate is dependent only on the first step. The second step, there are 2 reactants, but the reactant rate is not dependent on this. So if this was a slow step, then it would have been a bimolecular reaction. But because that was a previous step, which is slow, we had only one molecule participating, it became an SN1 mechanism, unimolecular. Clear? Now the order of reactivity of the SN1 reaction will depend on the stability of the carbocation. Carbocation is intermediate in this, right? So we said 3 degree carbocation is more stable than 2 degrees, more stable than 1 degree. Therefore, the reaction rate also happens in the same order. 3 degree more than 2 degree more than 1 degree. Is that clear? Then, among the halides, you know that I is a good leaving group. So when I goes out easily, we get the R plus, and once the R plus is formed, the SN1 reaction happens, and therefore iodides, that is alkyl iodides, are more reactive than bromides, are more reactive than chlorides, are more reactive than fluorides. I hope this is clear. So to summarize what we have done, in the SN1 mechanism, we have found that there are 2 steps, actually minimum 2 steps we should say, because the carbocation may undergo rearrangement. Next thing is, we don't have an attacking nucleophile, and the first step is a heterolytic cleavage to form ions, and those ions will be stabilized only by a polar protic solvent such as water, right? Then we said nucleophile is not an attacking nucleophile, and the nucleophile is waiting for the carbocation to form, right? And the second step is a fast step, right? And we have seen this order, 3 degree more than 2 degree more than 1 degree. So these are all the things that are characteristics of the SN1 mechanism, right? So are we in a position to take up the SN2 mechanism now? So in SN1 mechanism, we have all understood what is happening. There are 2 steps and how the final product is formed. Clear? One more thing that we need to note is that benzylic and allylic halides, they'll undergo only SN1 type of mechanism because their carbocations are resonance stabilized. So whenever we find that the carbocation is stabilized to a large extent, the reaction is undergoing SN1 mechanism. Clear? So let us look at the benzyl carbocation. Now this positive charge can get delocalized, right? We get a plus charge here, and like this we can make the positive charge move throughout the ring. So there is a delocalization of the positive charge. So positive charge is being shared by various atoms, and wherever sharing happens, each atom has got less load. The load of carrying the positive charge is less, right? And therefore the carbocation is stable. So this is resonance stabilization. Similarly, look at the allyl. So allyl is also stabilized, right? And if you see, both the allyl carbocations are identical. A C double bond C and attached to a C plus is common in both, right? So allyl and benzyl carbocations being resonance stabilized, they are easily formed. Therefore their parent halides, benzylic halide or allylic halide, are undergoing SN1 type of mechanism, right, instead of the other type. Now this is very important. if the alkyl halide is optically active, then the product obtained is a racemic mixture, means you get a pair of enantiomers. Now we got the carbocation there as an intermediate. Carbocation, you know, has a trigonal planar structure. So a nucleophile can come and attack this carbocation either from top or from bottom. So from top, if you get an object, from bottom you get an image. So you get a pair of enantiomers. And if this attack of nucleophile from top and bottom is almost of same probability, 50-50, then you will have a 50-50 mixture of enantiomers, which is nothing but a racemic mixture. So racemic mixture is a 50-50 or 1:1 mixture of enantiomers. And therefore, if one enantiomer turns plane polarized light to the right or clockwise, the other does anti-clockwise, so that overall effect is 0. That is what is a racemic mixture or a racemization. Clear? Racemic mixture is optically inactive. Next, we'll move on to the second mechanism, that is SN2 substitution, nucleophilic bimolecular. Right? Now let us look at the reaction rate, how it is dependent on. It is dependent on both the concentration of alkyl halide and the nucleophile. So how we can show this? Rate is equal to K into Rx power 1, nucleophile power 1. So order is 2. So in this case, the bimolecular, molecularity being 2 and order being 2 are coincidental. Means there is no hard rule that bimolecular needs to be order 2. Right? In this case, it happens. Now how does this happen? The nucleophile is going to attack the alkyl halide. So nucleophile is an attacking nucleophile. Right? Now, because here also the nucleophile is charged, right, or is polar, we need a polar solvent. But now we will use a polar aprotic solvent, because the nucleophile must not be covered by the solvent. So polar aprotic solvent. The nucleophile must not be covered by the solvent. The nucleophile must be free to attack, means it is an attacking nucleophile. And this mechanism happens in only one step. There we said minimum 2 steps, is it not? So here the nucleophile is going to attack the alkyl halide from a side which is opposite to that of the leaving halogen, because halogen is having some negative charge and nucleophile is also carrying electron density. So the nucleophile which is electron dense cannot come from the side where the halogen is also electron dense, is it not, because of repulsion. Therefore the nucleophile has to come from the opposite side or the rear side. Right? Now while it is coming and attacking this carbon, the X is about to go. So the outgoing nucleophile is about to go, the incoming nucleophile is about to come, right? And we get a transition state. We don't have any intermediates. So in SN2, there is only one step. Therefore, there is no scope for intermediates. There are no intermediates in this. Whereas there in SN1, we had carbocation as the intermediate, right? That was a 2-step reaction. This is a 1-step reaction, right? Here we have an attacking nucleophile. Here we have a polar aprotic solvent which will make the nucleophile free, not cover it. When it covers it, the nucleophile is not in a position to attack. So we are seeing to it that the nucleophile is an attacking nucleophile. We have not made the ions, because ions are stabilized only in a protic solvent. We have used a polar aprotic solvent. So the ions are not formed, right? And the nucleophile has attacked this carbon. While it is attacking, while it is getting attached to the carbon, the halogen is getting detached from the carbon. Clear? So it is partially bonded, right? The nucleophile is partially bonded to the carbon. The halogen is also partially bonded. In the next step, the halogen is gone and the nucleophile is fit. Clear? So this is what is happening in the SN2 mechanism. Now the nucleophile has to attack the carbon, means the nucleophile has to get a free space for attack, means the nucleophile has to approach the carbon, and while it is approaching the carbon, there cannot be any steric hindrance. So the groups that are attached to the carbon should not be bulky, right? And bulky groups, if they are there, they will block the way of nucleophile and the nucleophile cannot come and attack the carbon. So for the nucleophile to come and attack the carbon, right, as an attacking nucleophile, it has to find a way which is clear for attack. Therefore, the groups that are attached to carbon cannot be bulky, right? So steric hindrance has to be minimum. So what this SN2 mechanism depends upon, it depends upon, right, where there is minimum steric hindrance. So when the nucleophile is not finding it difficult to reach the carbon, it will easily reach. So primary alkyl halides or methyl halides, CH3X. CH3X is the best thing that can happen because carbon is having 3 hydrogens and hydrogens are the smallest atoms, is it not? So the nucleophile can come and attack this carbon when it is methyl, the best, followed by a primary, then a secondary, then a tertiary. Here, the opposite happened in the SN1. In the SN1, we depended on what? Carbocation stability, where 3 degree offered the maximum stability of carbocation. Therefore, the order was 3 degree more than 2 degree more than 1 degree. But here it is 1 degree more than 2 degree more than 3 degree. And here the methyl is even better than the primary because methyl has got only hydrogens attached to the carbon and hydrogens are the smallest atoms. Clear? Now, we are representing this SN2 like this. This is the transition state. It's not an intermediate. In SN2, there is no intermediate. The OH minus has attacked this carbon from the rear side and therefore will have a position opposite to what chlorine had. That is, chlorine is the outgoing nucleophile. So the incoming nucleophile is not occupying the same place where the outgoing nucleophile was there. It is occupying a place which is opposite to that of the outgoing nucleophile. So it is something like an umbrella on a windy day, right? Suppose umbrella was like this. It will turn upside down, right, on a windy day. So this is what is happening. There is an inversion. The configuration is getting inverted. But the word inversion will happen only when it is a chiral substance, when it is an optically active halide. So if the starting material is optically active, then we can say that it has underwent inversion of configuration. The word inversion is used only for a chiral substance which is optically active. What is a chiral carbon? A chiral carbon is one which is attached to 4 different groups, but here this all 3 are hydrogens here. So it is not an optically active substance. If it was optically active, then it would undergo what? Inversion of configuration. I hope this is clear. So this is a methyl halide which will offer minimum steric hindrance, as we said, because only hydrogens are there. Hydrogens are the smallest atoms. So the OH minus, which is the incoming nucleophile, is finding its way clear to attack the carbon from the rear side. Clear? Now, since the attack of nucleophile takes place on the side opposite, right, to that of the leaving group, there is an inversion of configuration, but this is used only when the alkyl halide is optically active. So start with an alkyl halide which is optically active, and that will undergo inversion of configuration in the SN2 mechanism. I hope this is clear. We have understood also the differences between SN1 and SN2, right? There we said that SN1 reaction is a 2-step reaction or a minimum 2-step reaction, and here we find that there is a 1-step reaction. There we got an intermediate, here we don't have an intermediate. There we had a polar protic solvent, and here we have a polar aprotic solvent, right? So like that we have points of differences which we have summarized now, right? This we have seen. Methyl halide is the one which is undergoing SN2 very easily because the path is clear for the nucleophile to come and attack the carbon. Now, before we do that, we have some time to spend on the stereochemistry of SN1 and SN2, which you have already seen. So it's only for the sake of completion. For an SN2 reaction, there is an inversion of configuration. So if you have a 2-bromo-octane undergoing an SN2 reaction, we get octane 2-ol. This minus is a sign of rotation. It's an anti-clockwise rotating substance, means the substance which rotates plane polarized light anti-clockwise. And this is the one that rotates plane polarized light clockwise, right? So in SN2 reactions, the nucleophile will attack the carbon from the rear side, side opposite to the halogen. That is what we have shown here. But keep in mind, this is a very, very important thing that you need to note, is that the sign of rotation has nothing to do with the configuration. Keep that in mind. So it is not that because bromine was here, it is a minus here, sign of rotation, and because OH has come to the opposite side, it has become plus. It has nothing to do. The configuration and sign of rotation are two different things. In this case, it's a coincidence, right? And it's a wrong coincidence. It should not have happened, right? We should not have taken an example of this type where the minus is becoming plus because there is an inversion. No, not because there is an inversion. Inversion is also taking place. The sign of rotation is also taking place. The change of sign of rotation is also taking place. So it is not connected. There is no connection between what? Configuration and sign of rotation. Keep this in mind. You have to internalize this sign of rotation. So we'll now move on to SN1 where there is a racemization which you've already seen. Clear? Now, as we have already seen that carbocations have a trigonal planar structure and the nucleophile can come and attack either from top or from bottom with almost equal ease. This is very, very important. And in the next slide, we are going to make it very clear what is actually happening. So, with almost equal ease, we said 50-50. It need not be 50-50 as you will see now. Because when the halogen was here and the nucleophile was attacking the carbocation was formed, but the X minus has not moved out completely. So, a nucleophile attacking from here is more than a nucleophile attacking from there, which is less, because a halide has not left the place. Here, are you getting the point? So, nucleophile is finding the rear side attack more than the front side attack, because in the front the X minus has not left the position. So, only when X minus moves out completely can the nucleophile come, is it not? So, it is not 50-50. So, the inversion is more than retention. This is giving retention. If it comes from the same side, it is retention. If it comes from the opposite side, it is inversion. In SN1, we thought that there is 50% retention and 50% inversion, but it is not equal. The inversion is more than the retention, right? That is what you can read from this. 100% racemization is found to occur only in rare cases, right? So, this point shows that it is partial racemization. The inverted product is more than the retention product. Clear? That you keep in mind. Now, having done all these things, we will now be in a position to take up the summary of differences between SN1 and SN2. Now, the first point is what? It's a polar protic solvent used in SN1 because it has to stabilize the ions formed. Whereas a polar aprotic solvent is used in SN2 because the nucleophile has to be left free for it to attack the substrate or the reactant. Now, we have a weak nucleophile. We don't have an attacking nucleophile in SN1, but in SN2, we'll have an attacking nucleophile. Then, the SN1 reaction is based on the stability of a carbocation. If the carbocation is stable, the substance will undergo SN1 reaction. Whereas for SN2 to happen, we need least steric hindrance because the nucleophile has to come and attack the carbon, right? The way has to be clear. So, bulky groups should not be there. So, steric hindrance has to be minimum there and SN2 is bound to happen easily. Now, we said in SN1 there are minimum 2 steps. Why minimum 2 steps? Because when a carbocation is formed, it may undergo also rearrangement if it is not stable. Therefore, add 1 step. But SN2 is just 1 step. 1 step reactions are also called concerted reactions or elementary reactions. Then we have racemization, right? We said it is partial racemization, but here it is inversion. Racemization means enantiomers are in equal quantities, almost equal quantities we can say, but here it is inversion of configuration, right? These are all the points that we have. There can be one more point added up, right? We said that there is an intermediate here and there is no intermediate. We say transition state is there. Transition state is there in any reaction. Even for SN1 we can show transition state. But what we are talking in SN2 is that there is no intermediate, there is only transition state. Here transition state and intermediate are there. In fact, transition states are there. Before the intermediate, after the intermediate, we have transition states. So transition state is common for all reactions. All reactions will have a transition state, as you have seen in chemical kinetics. Clear? So these are all the points of differences between SN1 and SN2. I hope it is clear. We have sufficiently done SN1 and SN2 reactions to enable us to check some questions which have come in the previous years, CUET as well as JEE main. The first question is, an optically active halide undergoing SN2 substitution involves what? Retention of configuration, racemic mixture, inversion of configuration, or formation of a carbocation. SN2 is a one-step process. There is no carbocation. So this is not going to be there. There is no racemic mixture, right? There is no retention of configuration. There is only an inversion of configuration. So SN2 substitution involves only inversion of configuration if it is starting with the what? Optically active alkyl halide. Clear? Next question. The compound that will undergo SN1 reaction with fastest rate is the one whose carbocation is the most stable. Is it this or this or this or this? So if I remove this Br as Br minus, I am going to get a primary carbocation, not very stable. If I remove this, I am going to get a secondary carbocation, which is not so much stable, right? This is 1 degree carbocation, this is 2 degree. This is a phenyl carbocation, very unstable, 3 will not happen at all. And in 4, we have a benzyl carbocation. We said benzyl carbocations are highly stable. It's actually a carbocation which is 2 degree as well as benzyl. So this is the most stable carbocation formed from this, and therefore this parent, that is 4, is the one that is undergoing SN1 reaction with the fastest rate. Clear? Next, for an SN2 reaction, the increasing order of reactivity, if you are looking at, there are 4 options. Now for SN2 reaction, what is required? Minimum steric hindrance. And we know that 1 degree is better than 2 degree is better than 3 degree. So this is 1 degree. This is 2 degree because this bromine is attached to a carbon which is attached to 2 carbons on either side. And this is 3 degree. And this again 1 degree. But there is some bulky group present here. Here we have 2 hydrogens, right? And this entire propyl is a straight chain. So it will not offer so much of steric hindrance when compared to this one, right? This is what C with a C and a C like this, right? So this is what an isopropyl group, right? And having 2 hydrogens and a bromine. This is D. D is also 1 degree, no doubt. So to compare between A and D, we said 1 degree is the best. So B and C are out. Now we have to decide between A and D. So in A, we have C, C, C straight chain, then attached to a carbon with 2 hydrogens, and then a bromine. Which is better? This is better, because this is a straight chain, will not offer so much of hindrance when compared to this, right? It's a bulky group here. So the 3 carbons are in the form of an isopropyl, in the form of a fork, right? Therefore this will give you more hindrance than 1. So 1 is the best. A is the best. So among the 1 degree, we find that N-propyl is better than isopropyl. Clear? Now we can say that this we have to follow now. So shall we say that we have to go according to this order. Less than means we are going to have the increasing order. Increasing order means which is the least? C is the least, followed by B, followed by D, followed by A. So we have option 4 as the answer. Clear? A is the best, followed by D. Then D is better than B, which is 2 degree. B is better than C, which is 3 degree. I hope this is clear. Yes. Now we have statement related questions. Statement 1. high concentration of a strong nucleophilic reagent with secondary halides which do not have bulky substituents will follow SN2 mechanism? Possible, because you don't have bulky substituents. And there is a high concentration of strong nucleophile, because for SN2, the reaction rate depends not only on the concentration of Rx, it will also depend on the concentration of the nucleophile. And when the nucleophile is sufficiently there around high concentration, it can come and attack the secondary alkyl halide because there is no bulky substituent. The way is clear. Therefore, statement 1 is correct. Statement 2. A secondary alkyl halide when treated with a large excess of ethanol follows SN1 mechanism. For SN1 mechanism, what do you require? Polar protic solvent, and alcohol is a protic solvent. So, secondary alkyl halide doesn't have any big bent towards SN1 or SN2 because it is in between 1 degree and 3 degree. 1 degree wants to undergo SN2, 3 degree wants to undergo SN1, and 2 degrees in between. So, it can be molded. We can mold the secondary halide to according to our requirement by choosing the solvent. So, when you have large excess of ethanol which is offering a polar, which is functioning as a polar protic solvent, it can do an SN1 mechanism. So, this is also possible. Statement 2 is also correct. So, we find that option 4 is the correct answer. Both statement 1 and statement 2 are true. Next question coming your way, probably the last for this session. Statement 1. CH3OCH2Cl will undergo SN1 reaction though it is a primary halide. We said SN1 is offered by 3 degree, more by 3 degree. Now look at this. In SN1, what is going to happen? You are going to lose the Cl in the first step. You get a carbocation. So take the carbocation. I will show the carbocation here. CH3OCH2 with a plus charge. SN1 is happening because the carbocation is stable. Now the oxygen which is present on the next, that is neighboring atom is oxygen. It can offer its lone pair, right, to form a double bond there, removing the negative charge on the carbon and sharing the positive charge. So when there is a sharing of positive charge, the load is less on each atom, therefore the carbocation is stabilized. So there is a resonance stabilization. Therefore this will happen. SN1 will take place because the carbocation is stabilized. Clear? Now look at statement 2. So statement 1 is correct. Statement 2. Though this is a primary halide, it will not undergo SN2 reaction. Now look at this. How is this? There is a carbon with 2 hydrogens and there is a chlorine. And what do you have here? You have a tertiary butyl group, which is a bulky group. Though we call this as primary, right? Among the primary, this is the worst because there is a tertiary butyl group which will block the entry of the nucleophile. So nucleophile will not be in a position to enter this, right, from the side opposite to Cl. So though this is a primary halide, it is only for namesake primary halide. It's like a secondary halide. It's like a tertiary halide rather, because you have a tertiary butyl group here blocking the way of the nucleophile. So nucleophile is not getting a clear path to come and attack this carbon from the rear side. Therefore, though this is a primary halide, it will not undergo SN2 reaction. This is also correct. So statement 1 and statement 2 both are correct. Statement 1 is correct because the carbocation is stable. Statement 2 is correct because the path for the nucleophile is blocked. There is this bulky tertiary butyl group which is not allowing the nucleophile to come and attack this carbon from the opposite side opposite to the halogen. Is that clear? So what shall we say is the answer? Both the statements are true. Option 2. Statement 1 is correct. Statement 2 is also correct. Now I hope with a small topic such as SN1 and SN2, we were trying to bring the concept in such a way that both SN1 and SN2 are understood and the differences are also understood, and the knowledge gained on this mechanism, on these mechanisms, has allowed us to solve some questions which have come in the entrance exam, right? I hope this session was useful. So see to it that you attend sessions of this kind, right? You can join or subscribe this channel which you've already shown for your various, what shall we say, requirements, whether it is a board exam or entrance exam. Entrance exam could be JEE Main, could be NEET, could be CUET, could be BITSAT, could be JEE Advanced, could be state level engineering exams, or even CBSE, right? CBSE or even State Board exams. So we have covered the concept in such a way that the understanding is of utmost importance. We have found that unless you understand the concept well, you will not be in a position to understand to solve the questions. To crack the questions, we need good conceptual understanding. So these are our details. For classroom coaching, you can approach us, right? Approaching any time center near to you. Or for online courses, there is this website available. So see to it that you follow us, check videos of this kind which are useful for your exam, right? Exam of various kinds, board or entrance, and make us part of your successful journey. Best wishes. Thank you.